All right, good morning. Welcome back. It's my great pleasure to be introducing this next session of 4 speakers. Our first talk is going to be entitled Sampling-Based Approximation Algorithms for Reachability Analysis with Provable Guarantees. And Lucas Lieberwin is going to be giving the talk. Let's see if I can figure this out.
My name is Lucas Lieberwin, and today I'll be talking about our work on approximate reachability analysis with provable guarantees. So when we think about motion planning, we often think about those very structured, easy to describe environments. However, in reality, we're often confronted with situations like this. So it's much harder to describe those situations. Objects are hard to describe, and there's very little structure in some of those environments. And also, usually, motion planning is part of a bigger system. And so, unfortunately, some of the offline safety guarantees that we can obtain from motion planning may not longer be viable in such situations. So this motivates the use of online verification techniques. And to this end, we can use reachability analysis. So with reachability analysis, for example, we can determine whether a plan is feasible or not before its execution, and then actually stop the execution before it happens. So in this paper, we consider reachability analysis. That is, for a given time step and initial set, we want to find all potentially reachable states from some set of initial conditions under some assumptions on the model of the dynamics. And in particular, in this paper, we're interested in finding an under-approximation to the true reachable set. That is, for every reachable set, we want to generate a subset from the initial set such that the reachable set of the subset of initial conditions actually is a good approximation in terms of the multiplicative error 1 minus epsilon in terms of the volume. Now, there's a few challenges involved with that. First of all, if we have reachability analysis, we have to reason about sets and how they evolve under the dynamics. Also, usually computations are performed in state space, so we have to deal with the curse of dimensionality. And finally, it's hardly ever possible to compute our reachable set exactly. So we have to defer to approximation techniques, and they usually exhibit some kind of trade-off between computation time and accuracy. Now, this trade-off actually has been extensively treated in a lot of related work. And in particular, in contrast to prior work, in our work, actually, we can explicitly state that trade-off between computation time and approximation accuracy in terms of the sampling complexity from the initial set. All right, so I now want to highlight 2 key insights to our algorithm. The first one being is that instead of computing the reachable set for the entire initial set right from the beginning, what we actually do is we decompose it into partial solutions. That is, we look at solutions from particular points within the initial set. And then what this gives us actually is that if the initial set changes, those partial solutions are still valid. So in particular, this motivates the use of some kind of lookup table where you can compute those heavy computations of reachable sets in an offline procedure. And during the online application of our algorithm, actually, we just need to retrieve the proper solutions. Now, the second insight into our method is that we not just sample random points from our initial set, but we actually sample points that are at least a distance delta apart from each other. One can think about this as follows. We can draw little circles of diameter delta around each point, and if we sample a new point and those 2 circles overlap, then we just reject that sample. So applying this iteratively gives us a so-called delta packing. And what we know in a delta packing is that actually any 2 points are at least delta apart, and at the same time, we cannot add any new points to that packing. So if we now go back to our reachable sets, we know that for 2 points from our initial set, they're at least a delta distance apart from each other. We would now, at least according to our intuition, expect that also the reachable sets are at least a certain distance apart from each other. And now what we actually show in the paper formally is that using certain properties of the dynamics, we can actually upper bound the volume of the intersection between those 2 reachable sets. And what this allows us to do is if the user gives a specified error guarantee epsilon, we can construct the appropriate delta packing with its appropriate size, which gives us a guaranteed under-approximation in terms of the volume. We actually now applied this algorithm to a Dubin's car model for a varying set of initial conditions. So depicted in green here, you can see some of the initial sets that we tested out. And then we computed a true reachable set as well as a uniform approximation. That is, we just uniformly sampled from the initial set. And we also computed the approximation based on our algorithm. And as we can see, we're actually able to outperform uniform sampling across all trials and also maintain our theoretical guarantees. All right, so with that, I want to thank you for your attention. I'd be happy to take questions later on.
Thank you, Lucas. Our second talk is entitled Towards Specification Guided Active Mars Exploration for Cooperative Robot Teams, and Peter Nilsson is going to be giving the talk.
Thank you.
Oh, hang on. Got it.
That's the one. OK, thanks. So this talk is about Mars exploration, in particular the Mars helicopter that JPL will send to Mars for the Mars 2020 mission, along with the more traditional rover vehicle. The idea is that by having a flying asset, we can improve mission efficiency by allowing exploration from above instead of looking from the limited view from the ground from the rover. This is one part of the problems we're interested in, is how we can coordinate between the rover and the copter in order for the copter to provide as much value as possible for a particular mission. And the second aspect is that we would like to improve autonomy by sending higher-level commands. Instead of saying, drive 30 centimeters forward, we would like to give higher-level task commands. We model the system using markov decision processes of different types. For example, we have two MDPs for motion for the rover and copter. We have a belief MDP for the environment belief that captures what we know about the environment that is unknown or partially unknown at the time of system deployment. And we have a specification of automaton that captures a specific task that we want to achieve with the system. We have different types of interconnections between these. We have, for example, exploration interconnections that when the rover or the copter move around and gather new information, that updates the state of the belief MDP. And here the specification automaton is obtained by translating a temporal logic formula to a specification automaton. We decompose this problem in time by first having in two phases. The first phase is an exploration phase, and the second phase is the mission execution phase, where we actually conduct the scientific task we're interested in. In each phase, only a subset of those four components are active. In the exploration phase, the copter and environment are active, and the copter explores the environment. And in the second phase, in the mission phase, the rover and the specification automaton and the environment are all active. So reducing the number of active components helps a bit with scalability, and it also makes a lot of sense if you look at time scales here, because the rover can drive for a full day, but due to battery constraints, the copter can only fly for a few minutes. And this decomposition also allows us to phrase an objective for what we want to achieve in the exploration phase. If we look at what can happen after exploration, we can be in three different scenarios. We can either have a very high confidence in being able to complete the task we had defined, or we can have a very low confidence, meaning that we should probably do something else instead because this task is, it has a low probability of being able to succeed. Or we can be in between, which is actually the least desirable here because that gives us the least actionable knowledge. So we define this reachability, this exploration reachability objective where we want to reach either of these two extremes. And we can then construct an algorithm for planning both the mission phase and then the exploration phase. For planning the mission phase, we first translate the specification into an automaton, and we solve the stochastic reachability problem that maximizes the probability of completing this task. We then obtain the mission success probabilities that we need to plan the exploration phase, and we again solve the stochastic reachability problem to maximize the likelihood of ending up in one of these two extremes. So as a byproduct of solving the problem in this way, during an execution of these policies, we can continuously monitor the mission success probabilities. And we can use that knowledge to make decisions whether we should continue with the task, whether we should abort a task, or if additional exploration is required or warranted. So in this example here, at the start of the mission, there was a high likelihood of finding a sample here, which was the given task. But it turned out that that region was empty. And then the probability will jump to somewhere in between, and we can then use exploration to try to again show that either the mission has a high likelihood of succeeding or very low. So in this case, the exploration was able to reduced uncertainty in environment. And in this case, it turned out that the task was possible to achieve because there was no obstacle in that region there, and there was a sample present at another target location further ahead. So we can then proceed with the mission phase and send the rover out to collect the sample at this location. So this was an example where exploration resulted in a high likelihood of specification satisfaction, which is what you see here to the left. Here to the right, for the exact same policy, but in a different environment, exploration results in a very low likelihood of mission satisfaction. And we can then abort the mission and redirect resources to something more promising. Thank you.
Thank you, Peter. So the penultimate talk for this session is called Safe Motion Planning in Unknown Environments, Optimality Benchmarks, and Tractable Policies, and Marco Pavone is going to give the talk.
Okay, so this paper addresses the problem of planning in unknown environments, where the obstacle space is incrementally revealed online, for example, through line-of-sight perception. In general, the motion planning problem entails finding a trajectory for a robot that is collision-free and minimizes some cost. And typically, the motion planning problem assumes a known environment. But in reality, the environment is often unknown beyond local perception. A key challenge is that, unlike the case of planning in a known environment, for planning in unknown environment, it's not even clear what an optimal policy to strive for is. Consider, as an example, a robot equipped with a line-of-sight perception that has to navigate an unknown forest environment. As the robot moves, it has to weigh the exploration of the unobserved environment with the exploitation of the observed environment in a way that is optimal with respect to the information available. A typical approach, a heuristic approach, is to continuously replan a motion with respect to the observed portion of the environment. But this is just an heuristic. What we want to do in this paper is to devise a theoretical framework to design planning algorithms for unknown environments that account for safety and efficiency in a principled way. So the first step is to introduce a notion of optimality for planning in unknown environments, with the goal of deriving a performance benchmark that tells us how well we are doing and how well we can do. Now, when the environment is known, it is straightforward to characterize the optimal cost of a safe trajectory as a solution to a constraint optimization problem, which entails minimizing a cost subject to collision avoidance constraints. But the situation is not so clear in the case of an unknown environment. First of all, it would be unfair to compare to the same benchmark used for the known environment setting. More importantly, instead of a benchmark for safe trajectories, one needs a benchmark for safe policies, as robots needs to decide how to act based on information that is acquired online through the perception module. Despite these complexities, we were able to write down a different constraint optimization problem that exactly capture the optimal cost that is attainable by a safe policy, where a safe policy is a policy that is guaranteed not to collide with any obstacles, regardless of the true hidden environment. And I do not expect you to parse this, but I'll be happy to discuss it in the poster session. Now, the second step is to leverage the benchmark for algorithm design. So the proof of the benchmark entails the characterization of a policy that is simple but brittle, in that it only performs well if it guesses the true environment. What we did was to characterize and devise a class of policies that is robust against inaccurate guesses of the unobserved environment. The class of policies that we came up with is pseudo-optimal, in that each policy in this class is safe, and if the prior information about environment is just the true environment, then the resulting policy is optimal. More importantly, the policies in this class have a performance that degrades gracefully as the prior information about the environment gets increasingly inaccurate. Now, so far, we have not discussed the computational aspects. So our next step was to merge techniques from approximate dynamic programming and sampling-based motion planning to approximate the pseudo-optimal class of policies in order to be able to compute policy actions in a few hundreds of milliseconds for a representative set of kinodynamic systems. We tested our algorithms on a variety of simulation environments, including a building environment where a car-like robot has to navigate narrow corridors at high speed, as represented here. As the robot moves, it has to constantly update its best guess about how to reach the goal. Note here how the robot takes a wide turn in order to assess whether the horizontal corridor is open while navigating at high speed. This is a completely emergent behavior from our optimization, which rewards just the right amount of exploration. By tracking speed with respect to time, you can see how our algorithms allow the robot to navigate through the building environment at a very high speed throughout, with safety guarantees and without prior information about the environment. So in conclusion, our paper has three main contributions. First, we introduced a benchmark for safe planning in unknown environments. We derived a pseudo-optimal class of policies informed by such a benchmark. And finally, we implemented this class of policies in a real-time manner. There are several directions for future research. Among other things, we're interested in extending our framework to the setting of perception noise and in using learning-based guesses for the unobserved portion of the environment. And I hope to see you at the poster. Thank you.
Thank you, Marco. Thank you, Marco. Our final talk of this session is called Probabilistically Safe Robot Planning with Confidence-Based Human Predictions, and Hamy Fisak will be giving the talk.
Thanks. Hi, good morning. So I'm going to be talking about how we can try to help robotic systems navigate safely around people. And this is a pretty important question, because when we talk about the impact of robotics, we really don't mean it literally. So throughout the talk, we're going to be using the running example of a human pedestrian and a small quadcopter vehicle. But more generally, we're interested in allowing humans and robots to safely coexist in whatever space. To do this, the robot needs to reason about where the human is going to be in the future and plan to stay out of the way. And a useful model that was initially proposed in mathematical psychology and now commonly used in robotics is what's called noisy or Boltzmann rationality. The human's actions won't necessarily be optimal, but they will be exponentially more likely the more efficient they are for a certain objective. For example, say that the human's objective is to leave the room. Then conditional on that, the robot can reason about the probability of her future trajectories. Unfortunately, no model is ever perfectly accurate, and this is particularly true for people, which means that eventually something's going to happen that the robot didn't see coming, and that can lead to a loss of safety. For example, suppose that somebody spills some coffee on the floor, and now the human's going to deviate to avoid it, but the robot has no notion of coffee spills. And so it'll keep predicting that the human's going to go straight to the goal, which of course she doesn't, and now the robot's in the way, eventually crashes into the human, and the human's very angry. This is a particularly cheerful human, so don't let that fool you. But the common observation is, if the human doesn't follow the model, we should be suspicious of the model rather than blame the human. So in particular, the Boltzmann model has this inverse temperature parameter, beta, that is typically kept fixed and thought of as how rational the human is. But instead, we propose estimating, or rather keeping a Bayesian inference of this model over time to keep track of whether the human is behaving the way we expect. And when they don't, what that means is that we should expect a higher variance in the future actions. And this happens naturally by the robot thinking of the human as being somewhat less rational. Instead of trying to look for the perfect human model, what we're doing is we're keeping a Bayesian belief on this scalar parameter, which is very quick and data efficient. So that is the human prediction side of things. But now, how do we translate this into actual safety guarantees for the physical robot? To do this, we need to switch gears a bit and talk about control theory. So in order to plan fast, motion planners usually use a simplified model of the robot's dynamics, but that means that the physical robot will have a hard time accurately following the trajectory. So in recent work, we propose using robust optimal control theory to solve the zero-sum game between a tracker and an evasive planner. And this offline Hamilton-Jacobi computation gives us a tracking error bound as well as an optimal tracking control policy that guarantees that the physical system can stay within this bound. We can now use that bound to plan very quickly in real time with an actual guarantee that the physical system will remain within this time-varying corridor and therefore stay safe. But now remember that our human predictions are both time-varying and probabilistic, which means that we need to use this worst-case tracking bound to reason about safety in probabilistic terms. there's a natural way to do this, which is when the robot considers some future state at time tau, say, it can use a probability distribution of the human state at that time tau, and now it can take its tracking error bound and project it onto the human state, and effectively integrate the total amount of probability mass of the human that intersects this bound. And that is equal to the probability of colliding with the human. So now the robot can, for example, reject points that have a probability of collision of more than, say, 1%. So let's see how this works in practice. Even if we keep this confidence beta fixed, you can see that the robot plans around the human when they seem to be in the way, and then replans for efficiency when they move out of the way. And this works well as long as the human is moving to one of the known goals. But when the human starts moving in a new direction, the robot will make some unreasonable prediction of how she's going to turn and go to one of the goals, which leads to unsafely closed trajectories. If instead we use Bayesian confidence, we observe a similar kind of behavior as long as the human is following the model, behaving in a way consistent with the model. But crucially, whenever the human starts moving in a way that seems arbitrary to the robot, we see how the robot automatically becomes less certain about where she's going to go next, and consequently plans more conservative trajectories. So revisiting the coffee spill example, we can see that as soon as the human starts deviating away from the straight line trajectory to avoid the coffee spill, the robot becomes less certain and sufficiently cautious to stay away from the human. So to wrap up, we're proposing using this inverse temperature parameter in the Boltzmann model as a natural scalar confidence indicator that we can keep track of very quickly in a Bayesian framework. And now we can combine the resulting predictions with this worst-case dynamic tracking error bound to obtain a probabilistic safety guarantee for the physical robot. Thank you very much, and I look forward to seeing you at the poster session.
Thank you. Can I ask all of the speakers to come up? And I'd like to commend them. I think those were 4 particularly clear talks. So let's see if we get some good questions. Questions? So we'll take a question, I think, from the orange box.
Hello, I have a talk for the last speaker. I was curious how well this technique scales with more than one person.
That's a great question, and we're getting it a lot. So the quick answer is the scaling really depends on your predictive model. And really, our approach sits on top of your predictive model, whatever that is. But in general, the beta estimation phase that we're doing is linear in the number of humans, and in fact, it's perfectly parallelizable. So that part scales really well. The really cool thing is that even if you have the simplest sort of predictive model of multiple humans and how they interact, which is to say that they don't interact and your predictions are independent, that's probably going to be a pretty bad model when they actually interact, right? But then what will happen is automatically when 2 humans stop to talk to each other or avoid each other, whatever thing, the model will automatically become more cautious because it'll be like, whoa, I don't know what these people are doing right now. So the robot is naturally going to adapt to that.
All right, thank you. I think we have another question from the orange microphone in this case.
I have a question for the first speaker. What kind of assumptions on your system dynamics do you need for your method to work?
Okay, so there's actually we don't really make assumptions. We more look at some of the properties of the systems, and so it's also an assumption in a sense. But the main assumption is that we define some form of Lipschitz continuity. And in particular, what we mean by that is that if you look at the reachable sets of 2 points, and they have a certain distance between each other, that also corresponds to like an upper bound in terms of the volume of how much they could intersect with each other. So it's kind of like a way for us to describe how much new information we gain if a certain point is different than another point we consider.
Thank you. I think we have the blue microphone.
Hi. Last speaker. Very nice work, by the way.
Thanks.
Do you have any benchmark that compares to the following very stupid strategy? If the human deviates, I just stop and wait till I get a new strategy from the human and then continue. Mm-hmm. How is it much more efficient, or do you have any quantification on that?
Well, so we haven't actually run an experimental benchmark, but I have a couple of thoughts on that particular strategy, which is, well, first, it's assuming that your robot can stop, which is true in many cases. If you have a quad rotor, it can sort of stop within a reasonable amount of space. But it's also assuming that it's safe to just stay where you are, right? Which might work in some cases if the human is seeing you and will automatically get out of your way, then that's fine. In some cases, though, you might become a sitting duck and just wait for the human to hit you, which is not always the best option. This is a more general approach, which means that if the human is just coming straight at you, you will replan to get out of the human's way. So, in a very simple case, you could show that this strategy will break down, that strategy will break down in simple cases, right? But yeah, one thing that we're looking into is also how do you robustify the system when you start having multiple robots, multiple humans, and how do you make sure that you retain feasibility over time so that your system doesn't suddenly go like, oh, I don't know what to do. Yeah.
Okay, we have time for just one more, I'm afraid. You'll have to hold yours to the poster session, Dimitri. Let's take from the green microphone, please.
It's a question for the last speaker. Thank you for your talk. Oh, here.
Sorry, where are you?
In the center.
Hi.
Thank you for your talk. I had a question regarding, do you come up with situations where you run into deadlocks? And is there a way to break a deadlock once it happens with your model? Some sort of like a nudge and move ahead kind of a strategy?
So I'm not sure what kind of, if by a deadlock you mean getting to a situation where you lose feasibility and the planner simply says, I don't know what to do. You could imagine if you had multiple humans, lots of constraints, that this could in principle happen. There's an argument which is, right now all safety guarantees are probabilistic, and they have to be because we don't know what the human is going to be for sure. But there's a natural way in which the robot keeps replanning as the human, we're doing this 10 times per second right now with updates on the human prediction. And so if the robot starts detecting a growing probability that this current plan is going to get it in trouble later, it'll eventually start, trying to replan and find a new one. So you can at least make an argument that before things get terrible, they're going to start getting slightly worse, and the robot should be able to plan around that. But actually finding recursive feasibility guarantees, it's really hard when you have uncertainty, but it is something that we're looking into.
Thank you.
All right, let's thank these four gentlemen.